All right, guys, so for this discussion post, I'm going to go through this problem from web work that deals with a logistic population growth. Um, just going to hop right into it. I'm going to identify some of the variables first, and then we're going to get into the actual finding P of t, and then we'll be able to plug our variables in and answer some of these questions down here. So looks like the lake is stocked with 300 fish, so that's going to be our P naught equals 300, and then our carrying capacity is represented by K, uppercase K, and that is 8,600, and then P naught, of course, is T0. But then we also have another condition here that they give us, that the number of fish is tripled in the first year. So we also have a second condition, because you'll see in a little bit we'll have two variables that we have to solve for. So we need two conditions. So we also have t, when t equals 1, if the fish tripled, we're going to have P1 is equal to 900. So these are some of our variables right off the bat. We're going to get into the derivation of P of t now. And this one's always kind of tough for me. We got some weird partial fraction stuff that's going to go on. So just get into it, you'll see. So I always like to start by writing it down so I can really understand what we're working with. 1 minus P over uppercase K. And I'm going to just get started by separating those variables. And we are going to have 1 over P times 1 minus P over K dP equals K, lowercase k. That's our constant of our growth constant, dt. And I'm going to do a little bit of manipulation over here to tune this up. This 1 minus P over K can actually turn into, that 1 is equivalent to K over K and minus P over K. And that can turn into K minus P over K. And then we'll plug that back in over here. And I'm going to go ahead and write our integral. So then we have the integral of, I'll start with our denominator. We have that P, and then we have that K minus P. And then I'm just going to, since we have a complex fraction over here, I'm just going to flip this K that's in the denominator. I'm just going to put that right on top. And that's going to be dP. And that's going to be equal to lowercase k dt. We're taking the integral of that as well. So our partial fraction over here, this is the one, it's always kind of tough for me. But I saw this really cool method. And we're going to start just by writing it out. I know it's going to look something like this. We're going to have something over P plus something over K minus P dP. And then I'm going to go ahead and just take the integral of K dt. It's an easy guy. We got K, T, don't forget your constant. And we're going to have a couple iterations of that constant. So I'm going to start with a C1. And we're back on the partial fraction over here. So if I'm looking at this P term in specific outside the parentheses, I'm thinking to myself, what do I have to do to that term to make the denominator as a whole equal to 0? And to do that, I'm just going to make P 0. And if I make that P 0, and if I make this p 0 and I also plug a 0 in here, I end up with k over k, and that's going to give me a 1 over this for that fraction. And that makes sense. It's just a constant on top. It's linear. This p over 1 is linear. And so is this. It's to the first power in the denominator, so we know it's just going to be a constant on top. So I'm looking, I come back up here, and I'm going to look at it and try and figure out the same thing. If I am looking at just what's in the parentheses over here, how am I going to get that equal to 0? It's going to need to be k minus k. So if I make p equal k, and I replace this p over here with a k, I end up with k over k again. So this goes to 0, and I end up with k over k. So I have a 1 again for that partial fraction. So now we're dealing with something that's should be pretty easy for us to integrate. So 1 over p, that's the natural log of the absolute value of p. And then I'm going to leave the sign out here just for a second, because we have the ln absolute value of k minus p, and then the derivative of this denominator here is going to determine our sign, and the derivative of k minus p with respect to p is -1. So I'm going to throw a negative sign in there, and that's going to be equal to our kt plus c1. And we have some natural log rules here we can put into play, and we know that the natural log of the absolute value of p minus the natural log of the absolute value of k minus p is equivalent to p over k minus p. And of course, I didn't say it out loud, but we're keeping the absolute value sign symbol here, and that's still going to be, our right side has not changed. And at this point, I am going to exponentiate the function. So if I put an e under everything, the natural log is going to go way over here. Don't forget not to lose those absolute value signs. Set that equal to, and then we're going to have e to the c1 multiplied by e to the kt. And then I'm going to get rid of those absolute value signs. We're going to have our first c change here. K minus p is equal to c2 e kt when c2 equals plus or minus. So this plus or minus that I'm putting on here, this plus or minus is how I got rid of the absolute value signs. So C2, when C2 is equal to e to the c, plus or minus e to the c1. So we had our first constant change there. Fire up a new page, and we're going to keep going. So our next step is, what I want to do is flip both sides. So I get that p that's on top over here. I get this p in the denominator. It's going to make things look a little bit more simple. So I'm going to flip both sides. So I'm going to end up with k minus p over p. And I'm going to set that equal to, this is going to become 1 over c2 e to the kt. And then what I can do here is I'm going to have another iteration of my constant. So this one's a little confusing. So when, so I'm going to write it out first. So we have k minus p over p is equal to C3 times e to the negative kt, because we brought that up, and that's when C3 is equal to 1 over C2. So that takes care of that, and we are going to continue to solve here. And what I can do now is I can just multiply that p in the denominator over, so we end up with k minus p is equal to C3 p e negative kt. And now I will add the p over to the other side, and we end up with k is equal to C3 p e to the negative kt plus p. And then next step, I'm going to factor that p out, so we have p on its own, because we need to get this equal to p, right? That's the goal. It's sometimes I'll get lost when I'm doing these, and I'll forget actually what I'm doing. So negative. So we got C3 negative e to the negative kt, and that's going to be a plus 1. And we got the p on the outside. And now I'm going to divide all this over to the other side. So we end up with, I'm going to move some stuff around. So I'm going to end up with p of t is equal to k over 1 plus C3 e to the negative kt. And now this is something that we can actually use. So remember, our k is equal to uppercase k is equal to 8600. And we're going to be trying to solve for our c first. So at t equals 0, p equals 300. So that's our initial condition. So I'm going to go double check those numbers, make sure we're good. So yep, I got our k, 8600. Initial condition right here. Looks good. So first we're going to solve for c with that for that p naught initial condition. And then after we solve for c, we'll be able to go back, and then at that point we'll be able to solve for lowercase k, our constant lowercase k, and then we'll be able to actually have a complete p of t, because right now we're just looking at a general solution, and because we have a c and the k missing, we're going to need to go through two conditions to get that all solved for our particular solution. So we'll just jump right into this. P of t is going to be 300. We're going to throw in that 8600 up here. And then we're going to have a 1 plus c. And then it's really going to be e to the 0 down there. So just move over one step. And this becomes 300 is equal to 8600 over 1 plus c. And then I'm going to multiply that 1 plus c up to the top. And so I'll have 300. I'll write this a little closer. 300 plus 300c is equal to 8600. And then now we're just solving for c. So it should be easy money. feel comfortable doing that math in my head. And then we end up with 8,300 over 300. And grab my calculator here. 8,300 divided by 300 is 26 and 2/3. Or if you want to write that as a fraction, equals 83/3. So that's our C. And I think I am going to use the decimal version of this. And I'll carry out with 5 decimal points just for accuracy. So we got 27.66667 is our C value. And I'm going to go ahead and plug that back into our P of T. We're getting closer to our particular solution. So our P of T now is still that, still got the 8,600 on top. And we have 1 plus 27.66667 e to the negative kt. So we're getting closer to a particular solution here. So we're going to look at our second condition that we have. So if you guys remember, P of 1 is equal to 900. So that's going to make our T equal 1, which is nice. It's going to make things easy for us. We're going to plug that 900 in over here. 900 equal to 8,600. It's pretty much just wash, rinse, and repeat here. 1 plus 27.66667 E. And I'm just going to get rid of that T. We're not looking at it. Negative K. So now I'm going to make a new page. I'm going to bring this down here. I'm going to multiply our denominator up. And we end up with 900 plus 24,900 e to the negative k equal to 8,600. Gonna subtract the 900 over to the other side. And we end up with 24,900 e to the negative k is equal to 7,700. And let's see, what do I want to do here? So I'm trying to decide on whether or not I want to move that e down now and multiply it over, which I think that's what I'm going to do. So I'm going to rewrite this as 24,900 over e to the k, and then I'll be able to multiply that over, and I end up with 24,900 equal to 7,700 e to the k, and I'm going to divide that. I don't know if I like the way this is looking here. 3.2336767 is equal to e to the k. I'm going to take the natural log of both sides. No, that's not what I wanted to do. So I'm going to go back. Not do that, because I know that's not going to give me the right answer, because what I'm looking for here is the natural log's going to be, I'm going to be taking the natural log of a fraction, which I know is going to be less than 1, so it'll be negative. And then I have a negative k, so it'll cancel. So that wasn't going to work out, e to the negative k. So I'm going to divide, I'm going to have e to the negative k is equal to 7,700 over 24,900. And now I'll take the natural log. So I end up with the natural log and negative k equaling natural log of, let's see, divided by this simplifies a little bit. We can get rid of the zeros, so we end up with a natural log of 77 over 249. A little easy to write. And then that's actually going to equal negative k is equal to 1.7, sorry, negative 1.17365, and then our negative signs will cancel, and this ends up being our k value. So now we can rewrite our particular solution as P of t is equal to 8,600, our carrying capacity, over 1 plus that 27 2/3 e to the negative, we're going to keep that negative sign, 1.17365 times t. So now we have our particular solution. We should be able to answer any questions above with that. Let's go see if we got that k value right. Yep, so it looks like we got the k value right. And they're asking for the particular solution. Let's see if we got that right. Yeah, looks like WebWork did round me off when it marked it correct, but we got the 8,600K on top, our 27 2/3 multiplied by E, that negative 1.173T. And the final question here is, how long will it take for the population to increase to 4,300, half of the carrying capacity? So essentially, we know our P of T is going to equal 4,300, and we are looking for T. So let's go back down to our particular solution and put that thing to work. They're looking for, I'm just going to rewrite it so I know, don't get lost here. Looking for 4,300, and T is unknown. So I'm going to plug in 4,300 is equal to 8,600 over 1 plus 27.66667 E negative 1.17365 T. All right, we're going to multiply up again. So we got 4,300 first, and then we're going to have that times 27 2/3, and that comes out to 118,966. Let's ugly 6. Lots of ugly 6s. 118,966.681 e, the negative 1.17365 t equal to 8,600. And then that's an easy one, so we end up with 118,966.681 e negative 1.17365 t equal to 4,300. And then we're going to divide that out. So we're going to take 4,300, just trying to get e alone, and then so we can take the natural log. And so we're going to take 4,300, divide it by that 118,966.681, and we end up with e to the negative 1.17365 t is equal to 0.0361446, right? 0.0361446. Yep. All right. And then natural log, we get that negative 1.17365 t down, and we have the natural log of 0.0361446, and that's going to be negative. Again, less than 1. We're going to divide over our 1.17365, and we end up with the negative natural log of 0.0361446 over 1.1735, and they're looking for years, and that's not a very friendly way to tell somebody how many years you're looking for. So we're gonna get the non-exact value for that, and round off to a reasonable number of digits. So just gonna crunch this really quick. Get the natural log of 0.0361446 divided by 1.17365, and our negatives cancel, and we end up with 2.8289 years. And do you really need that many decimals for when you're telling somebody years? I don't know. Let them tell you. So let's go back up there and check our answer. So we're looking for somewhere in the ballpark of 2.83. And we'll check that. Money. All right, cool. So, yeah, I think this was a really good one to go through. I mean, at a glance, this logistic equation isn't super complicated, but that's just more salt in the wound if you lose points on it somewhere else. And to get through this problem, if you don't have the equation form memorized for P of T, you kind of need to know, or not kind of, you need to know a lot of techniques from all the years through calculus. So, I mean, as you can see, we had some partial fraction decomposition here, and juggling around all the different C values, keeping everything straight. So this problem had a lot of ins and outs, and a lot of places where you could have taken a wrong turn and lost points. So that's that. We ended up finding our general solution first, plug in our initial value P naught to find C, and then after you find C, you can plug everything back in again with your second value to find your particular solution. And then, forgot a parenthesis here, that is not a C, parenthesis. Yeah, and after you find your particular solution, it's pretty easy from there. You can kind of just plug and chug and finish answering any of the other questions that the problem might have. So if you made it all the way to the end, I hope you learned something. And this was fun. I know this helped me. And I won't be losing any points on a logistic population growth problem anytime in the near future. So good luck on exam 1, everybody. Thanks for watching.